Welcome to Finite Element Analysis lectures by Civil Thinking, and this is our another class, and in this class we will see what is meshing and all the basic things about meshing. We will learn those things. Okay, now before I move on, I suggest you to please watch the video lectures on finite element method one by one as in the playlist so that you understand better. The playlist link is in the description, or also you can click on the pop-up on your screen. Now coming to the today's class. Now in this class we will see about meshing. Now I have already given you a small idea in the previous classes what is meshing. So in this class we will elaborate on the meshing techniques and all the aspects of meshing. Now first of all, the basic question is what is meshing. Okay, so meshing is basically when we discretize a continuous body into finite elements. Okay, for example, you have a continuous body like this, and what you do, you discretize it into small elements. Okay, now these are the elements, and they are treated in such a way that we will find our required property, engineering property on these nodes. Okay, so meshing is basically what? Dividing, because it is a continuous body, dividing it into discrete number of elements. Okay, so if I write here what's about meshing, I can write meshing is the process of dividing a continuous body into discrete elements with the help of some basic geometric elements. Okay, so this is meshing. Basically what we do, we use some basic geometries, like this is a square, right? Or it can be line, or a chord element, or a triangular element, or other elements which we will see. Okay, so basically the main concept is a continuous body gets divided into discrete number of elements. Okay, why? So that we can analyze the body at only a few points. Okay, or nodes, which makes the analysis simple and less time consuming. Okay, because in the meshing what we do, because we only analyze the property at only few points. Okay, this way our the continuous body gets simplified, it gets reduced to few elements, and our computation time decreases. Okay, so let's move on. Now why do we carry out meshing? Okay, now basically when you look at a continuous body, if I write here continuous body, there are infinite number of points, right? So because in finite element method, what is it? It is node based, right? We find the results on points. Okay, or nodes. Okay, now what happens when the number of points are infinite? When they are infinite number of points, okay, so FEM will be impossible. Okay, it will be impossible because you had to carry out on infinite number of points. Okay, so but what we do, since we carry out meshing, we get only few or finite pointers, right? Then FEM analysis is possible. Okay, so basically what I am trying to say is, because you on a continuous body you have finite number of pointers, right, the nodes. But when we do meshing, okay, for example, when we do meshing, for example like this, right, then there are only, for example, 1 2 3 4 5 there are only few number of nodes, few number of pointers, and because FEM is basically what we do in finite element method, we find the results on pointers or nodes, okay, because it is this point based or node oriented, because we get a finite number of points, right? So the FEM analysis is possible, okay. So if I write here about this, why do we carry out meshing? So meshing converts a continuous body into a finite number of elements so that the FEM analysis is possible, right? So this is the main reason why we do meshing, okay. So now I told you we use elements, okay. Then we use elements in the meshing, and there are multiple types of elements like 1D element or 2D element or 3D element, okay. 1D, 2D and 3D. And yes, there are some special elements too, but I don't think this is suitable time right now to talk about those, okay. Right now it's better to keep the flow of understanding, okay. So what are they? These are basically the elements, okay. For example, you have a body, okay. You have this body. Now you can represent it with the help of lines, okay. This is a 1D element, okay, because it's the one dimension is longer, right? Okay, now you can also represent it with the help of two elements like this, okay. Now what is this? These are 2D elements, right? It is like this, right? So this is 2D element, okay, because the the two sides are comparably simple. Comparable. The magnitude of length is comparable, okay. For example, this is 2 mm, this can be 2.2 mm, so they are almost proportional. When we have two dimensions are proportional, so it is a 2D element, okay. Now the same body we can analyze it like a 3D, okay. If I draw it here, okay. Now this is, if I discretize it with the help of 3D elements, okay, so we get like we get a 3D element, okay. Each is like a brick, right? So this is 3D. In 3D, the dimensions are, all the three dimensions are comparable or proportional, okay. So we will talk one by one about all of these, 1D, 2D and 3D, okay. So let us move on and begin one by one. Now what happens in 1D? 1D is, for example, let me x is greater than yz. Let me show it here. For example, you have, let us say this is x-axis, this is y-axis, and this is z-axis, okay. Now what happens? Now when you have a body like this, okay, now you can see this is the x component, right, and this is the y, and this is the z, right. Now you can see the x length is too much more than y and z component, right. So when such a thing happens, we use 1D element, okay. So what happens when you have a beam, okay, for example, you have a beam here, okay, this is a beam, okay. Now because in this the one dimension is larger than the other two or the cross section, So we can represent it with the help of a line element. Okay, then maybe we will discretize it, but the thing is that we will represent when one dimension is more than the other two dimensions, then what we do, we represent it with the help of a line body. Okay, with the help of a line element. Okay, so now the first thing is always to do, okay, so when you have a 1D body, so first thing is you have to convert it into a line element. Okay, line elements. Okay, so and then what about this cross section? Then what we do, we provide additional data. In the additional data, we provide the value of y and z. Okay, for example, first we define the x. Okay, because x is the length of the line element. Okay, we always define this first. Okay, then y and z are not defined the same way as this. Okay, so first we create the length in the geometry, we provide this length. Okay, because the x length, okay, this is the length of the line. Okay, so in the geometry we draw and we provide this dimension. Okay, then as an additional data we provide the cross section. Okay, for example, this is y and this is z. Then in the additional data we provide y and z details. Okay, the cross section details. Okay, so as I have told you, when do we use this? We use this, let me erase all of this. Now where do we use this? We use it in things like beams, or you have a column like this. Here also you can see, for example, if this is y, okay, then it has some cross section, for example x and z. Now here y is greater than x comma z, right? Because this is the condition, so we will represent it what? With the help of a line element. Okay, of course we will discretize it. Okay, that was a column. Okay, then there are truss members. For example, you have, let me erase this first. Now when you have a truss, okay, when you have a truss, okay, you can see, for example, this element, its length is more than its cross section. Okay, so we represent all of them with the help of line elements. Okay, then we have what? Then we have suspension cables. Maybe you have seen some bridges where we use, like, for example, okay, then we use these suspension cables, right? Okay, now these suspension cables, you can see the length, one dimension is larger than the cross section. Okay, so because one dimension is larger than other two, so we use what? We use 1D elements. Okay, so let us move on. Now the 2D, what happens in 2D? For example, when you have a body, okay, for example, you have let me construct, draw. Okay, let me draw this rectangle. Okay, let us assume this is a slab. Okay, this is a slab. Okay, this is a slab. Okay, now you can see what happens in a slab. Let us say this is x dimension and let us say this is y dimension. Okay, now what is this z dimension? Is this, right? Now you can see here x and y, right, they are approximately equal. Okay, or or in a more appropriate sense, I can say, if two dimensions x and y are highly greater than the other dimension, okay, because the two dimensions are more than the third dimension. All right, so when two dimensions are more than the third dimension, then we use 2D elements, okay, because they are x is 1, y is 2, okay. So in this case we use 2D elements, okay. Now what happens in 2D elements, basically we, any software which works on FEM, basically it draws a plane in the middle, okay, 2D plane in the middle, okay. So this plane, it is drawn in the geometry, okay, or in any CAD software. Then for example, let us say the z dimension is thickness, okay, the thickness, then half of the thickness is shown on the top of this plane and half is thrown to the bottom of this plane, okay. So basically what we do, if I say it in a more meaningful way, the thing is that in 2D we always in the geometry we define two dimensions, okay, for example x and y, we define these, okay. Then what is the third, the thickness, all right, the depth or thickness, whatever you call it, that is the additional data, right, that is the additional data is what, z component, right. So I had defined x and y, then in the geometry, then the additional data is provided, okay, the z component is provided as the additional data, okay. It's not necessary z, for example, let's call this as z, then this is y, this is z, then the other dimension will be x, okay. So the main thing is the two dimensions, okay, the two dimensions are provided in the geometry and the third dimension is provided as what, as additional data, okay. So where do we use this? As I have told you, we can use this in for example slab, or we can use this in floor, where two dimensions are more than, wherever you see this condition where the two dimensions are more than the third dimension, we use 2D elements, okay. Then the thickness is distributed as half to the top, okay, half to the top and half to the bottom, okay. So this way we get, okay. Anyways, I hope you got the basic idea, so let's move on. Now when is 3D, now in this case when they are approximate, all the three elements are approximately equal, okay. For example this cube, okay, for example this is x dimension, this is y, and this is z dimension. Now you can see x is approximately equal to y, it is approximately equal to z, okay. So because they are comparatively equal, then what we do, we use 3D elements, okay. So also we use 3D elements where we have what, where we have the three dimensions comparable, okay. So we use these kinds of tetra, penta or hexa or pyramid. But where is it important? This is important where we have the properties, the analysis, or is important in all the three dimensions, okay. When we have to carry out the analysis so that we can find some properties in all the three dimensions, then we use 3D, okay. But remember, the computation time will be high, okay, because when you use 3D there will be more number of nodes, okay. So I will explain these pointers one by one. Now let me explain these first. Okay, now we have 1D element. Okay, 1D element, it is a line. Okay, then we have a 2D element. Now 2D can be tetra, or it can be what, triangular elements, or we call them as tria. Okay, now tetra is what, when you have 4 number of sides. Okay, for example this. Okay, now how many nodes are here? 1, 2, 3 and 4. Okay, now how many elements are in 1D? Only 2, right? 1D element, 2 nodes, right? Okay, now this is 4 nodes. Okay, now if we want to further increase the efficiency, we can induce one more node in the middle of each. Okay, then we have total how many? 1, 2, 3, 4, 5, 6, 7, 8. Okay, then we get 8 nodes. Now this is tria. Tria is triangular. How many nodes are here? 1, 2 and 3. Okay, 3 nodes, or we can place one even more. Then we have 6 nodes. Okay, then we have 3D. 3D, for example, 3D, when you extend these basic geometries, okay, into the other dimension, you get 3D. Okay, for example, you had like this, you had tetra. Okay, now when you expand it in the 3rd dimension, okay, so this becomes what, tetra. Okay, so how many nodes are here? 1, 2, 3, 4, 5, 6, 7 and 8. Okay, 8 nodes. Okay, now similarly we can increase number of nodes at the middle of each. Okay, then how many we will get? Because it is 1, 2, 3, 4, 5, 6, 7, 8 and 8 and 8 is 16 nodes. Okay, then in the 3D, now when we expand this in the 3rd dimension, this tria, what we get? We get pyramid. Okay, or we get penta, for example. Like this. Okay, then we get these nodes. Okay, how many nodes are here? 6 nodes, right? Okay, or if we increase further, we get what? How many do we get? This is 6 and plus 6, right? We get 12 nodes. Okay, then we can also improve it like this. I mean, extend it like this. For example, we have this. Okay, 1, 2, 3, 4 and 5. Okay, this is 5 nodes. Okay, then we can increase 6, 7, 8, 9. Okay, then we get 9 nodes. Okay, so these are 3D. They are basically what, the projection. When we extend the 2D into 3rd dimension, we get the 3D elements. Okay, okay, we also, these we call them as brick elements because it looks like a brick. Okay, so do I have to say anything more about this? Yes, computation time. Now let's talk about computation time. Okay, now because in FEM we carry out calculations on nodes. Okay, so more the nodes, right, more will be the calculations, so more will be the computation time, right? So time is directly proportional to the number of nodes. Okay, so if you have less time in your project, you can use simple simple geometries, so that you have less number of nodes and you will get less. Okay, now when you have more time, or you need more what we call more flexible or more detailed analysis, okay, then you can use 3D elements. You can increase the mesh density, you can increase the number of nodes. The computation time will be high, but you will get more accuracy. Okay, so again we use 3D in where the calculations are important in all the 3 dimensions. Okay, for example, this is soil, okay, and then you have a foundation on it. Okay, foundations or pile foundations or anything where the interaction between the lateral soil, okay, also matters. Okay, so here you need the results on all the 3 sides, you will use 3D. Okay, now in some places we need the results on only 2 sides, you use 2D. Okay, and sometimes you need only result along only 1 dimension, then use 1D. Okay, so let's move on. Can we solve the same problem using different elements? Now if you have this beam, okay, now can you solve this using 1D element, 2D element or 3D element? Can we? The simple answer is yes. Okay, but what is going to happen if you use 1D analysis? If you use 1D elements, you will have less nodes, right? So less time, it will take less time to solve this problem. Okay, now if you use 2D elements, so there will be more nodes, there will be, of course, it will take more time. Okay, now if we use 3D elements here, then we will have even more number of nodes and computation time will be very high. Okay, high time. Okay, so for example, let us talk about this. Now when we talk about 1D analysis, what we do, we represent this with the help of a line element. Okay, this beam we will represent it with the help of a line in 1D analysis. Okay, then as an additional data we will define this cross section, right? This is the cross section and this will be in additional data. Okay, now if we talk about 3D analysis, 2D analysis, we can represent this with the help of 2D, but what will be the additional data? Additional data will be this one, right? So let's for example call it as width B. Okay, so additional data will be width B. Okay, now we can also represent it with the help of 3D analysis. Okay, in 3D analysis do we need any additional data? No, we don't need, because we define all the x, y and z dimension in the geometry and there is no need for additional data in 3D, right? Because in 1D what was missing, we represent the length, right? This is the length, we represent this length, but what about other two, for example D, B and H? So as an additional data we provide it. Okay, now in 2D analysis we define, for example, we define the L and the H, right? But what about B? So we define it in the additional dimensions. Now in the 3D we will define the L, we will define what? The B, and we will define the H. Okay, so we don't have to use anything as an additional data. Okay, so when we carry out the meshing, okay, so it is going to be something like, for example, if we use brick, okay. So this is going to be, okay, it is going to be something like, for example, something like this, right? So of course here will be, see, 1 2 3 and 4, we have 4 nodes here, right? Now let's count number of nodes here. 1 2 3 4 5 6 7 8 9 10 11 12 13 and 14 nodes here, right? So C only 4 nodes and C only 14 nodes. Where we will where it will take less time? Of course, at less number of nodes. So 1D will take less time, right? So 1D will take less time than 2D. Now let's talk about 3D. How many elements nodes are here? 1 2 3 4 5 6 7 8 9 10 11 12 13 14 15 16 17. Okay, so all of this you have to count. Okay, there will be a lot. Okay, of course more than 14. Okay, for example, let me guess, maybe 50. Okay, so we have, for example, 50 nodes here. I didn't count. Okay, this is just for example. So 50 nodes or more, so we have to calculate the results on more number of nodes, right? So of course it will take more time. Okay, so the least amount of time is taken by 1D and the highest is taken by 3D. Okay, so then you have to decide based on the project, based on your time, based on what you need, okay, why you want to carry out analysis, but you have to use whatever it takes for the analysis. Okay, whatever the result you want, based on that you have to choose the element, okay, or based on the time. Okay, so let's move on. Now let's talk about meshing in the critical areas. Okay, now what happens, when you carry out meshing? For example, you have a body like this. Okay, when you carry out the meshing, now it is symmetric, right? It is same. Okay, there is no difference. Okay, so when you carry out the meshes and you run analysis, okay, so this is first run. I mean, when you run the analysis for the first time, okay, this is first run. Okay, you will get the results. Okay, you will get the results. Okay, then you will see something, more red color somewhere. Okay, when you see more red color in the analysis, what does it mean? It means the result is very high there. For example, if we talk about stress, okay, for example, you are analyzing this body in in any FEM software like ANSYS or something, or ABAX. Okay, what happens? You see the stress diagram and you see some red color somewhere. Okay, it means the stress is very high there. Okay, the stress is so much high. Okay, but your meshing is very poor meshing. Okay, it is not dense. So what we will do, instead of increasing the mesh density everywhere, okay, instead of increasing the mesh density everywhere, you will not do this. Okay, instead what you will do, you will increase mesh density where? At this point. Okay, because you have more red color here. Okay, it means the the stress is high there. Okay, so why you will increase the density everywhere? Okay, because then it will uselessly increase the computation time. Okay, so if your focus is to see, for example, now let's talk about a beam. Okay, now when you apply a load, okay, you are interested in for example, stress at this point. Okay, so instead of increasing the mesh density everywhere, what you will do, you will increase the mesh density only here. Okay, you will increase the mesh density only here. Okay, so that your computation time is saved. Okay, of course you can increase the mesh density everywhere, right? You can increase the mesh density, but you don't have. Why? No need, right? here you need more accuracy. For example, more accuracy, so let us increase the density of meshes here. Okay, similarly, for example, now this is the critical area. Now critical areas can be the defects, the holes, or your point of interest, okay, or connections. They are basically the critical areas. For example, you have a hole here, this is the first, okay, okay, then you carried out the analysis and you see in the analysis we have more red color here, okay, more red color here. Now the more red color is very high, right? It means you are going to increase the density in this area, okay, you will increase as shown here, okay. Instead of you see the stress is very much high here, so you just increase in small area around this, okay. You didn't increase here too, right? You didn't do that. You increase the mesh density at the critical area, okay. So similarly, for example, I have done this for one of my clients. I have done this analysis in the ANSYS and it was a 3-point bending test, okay. So it was basically a beam with a notch and we needed to find the compliance and the stress. So what I did, if you can see, if we can try to zoom in, as you can see, I have kept the meshing loose here, right? Because I don't need results here, so why I will keep it high density. The same thing, I cannot just leave it empty, okay. I cannot just let this without any meshing, because then the ANSYS will treat it as continuous body and there will be infinite number of pointers and there will be error, okay. So you cannot just simply leave some areas without meshing, okay. Don't do that, because then the ANSYS or FEM software, it will treat it like what? It will treat it like a continuous body, and in continuous bodies we have infinite number of pointers and that's it, okay. So what I did, I kept the meshing poor here, right, in these areas everywhere, but here, because this is a notch here, this is a critical area, as you can see, I have increased the meshing. Alright, I have increased the meshing in this area, right? I have increased the density, okay. So this is what I mean to say, okay. So that's it for today, and if you have any questions, please comment, and you can also contact me if you need any help or if you are facing some difficulty in your project. So that's it for today. See you in the next class. Thank you.